we discuss eventual leader election omega. So eventual leader election omega means that all processes will eventually agree on a single process as a leader. So eventual leader election omega and diamond P, the eventual leader detector, are quite similar. As we can see, diamond P weakens the perfect failure detector P by only provide eventual accuracy. In the same manner, omega weakens LE by only guaranteeing eventual agreement. So here is the properties of LE, and now the properties of omega is very similar. It has eventual completeness, which eventually every node will trust some correct node or process. It does not have local accuracy, but it has agreement, but eventually. So eventually, no two correct processes trust two different correct processes. Let us look to the implementation of the eventual leader election omega. So omega has one indication event, which is just trust some process PI. Omega uses an eventually perfect failure detector, diamond P. And if you remember, diamond P has two events. One event is to suspect a process, say PJ, and another event when the suspicion is wrong to restore the process PJ. So this is our setup. And the properties we want to prove: eventual completeness, eventually every correct process trusts some correct process, and eventual agreement, eventually no two correct processes trust different correct processes. Now let us look to the implementation of omega in the process crash stop abstraction, where a process can fail by crashing. In this case, omega is obtained directly from diamond P, and it is quite simple. So each process trusts the process with the highest rank among all processes not suspected by diamond P. So we use the max rank function that we used for the perfect leader election LE. And we trust the one with the highest rank. And just eventually, exactly one correct process will be trusted by all processes, because this property we get by the eventual accuracy of diamond P. And that's it. So it is quite simple. So here is the algorithm. We have an instance which is omega. You can see it here. And we use an eventually perfect failure detector, as you can see here. Initially, the list of suspected processes is empty, and the leader is undefined. And whenever we get a suspect event from diamond P, we add the process, if it was P, we add the process P into the suspected list. And whenever we get a restore event from diamond P, we remove the process P from the suspected list. And we take always the max rank function on the set of alive processes. And if the leader change, then we assign the leader to the max rank of the current non-suspected processes. And then we trigger a trust event to the rest of the application. So here is trust. So this is the algorithm. And as we said, eventually all the suspicions will be correct, and we left only with alive processes, and the max rank function will pick the one with the highest rank. A quite interesting algorithm, on the other hand, is omega for the crash recovery model. First, remember that in the crash recovery model, a process is correct if it never fails or it fails a finite number of times. So processes that fail and recover infinite number of times, these are faulty processes. So can we elect a recover process then? The answer, of course, is no, if it keeps crashing infinitely often, but that is a faulty process, and we don't want to elect a faulty process. So what is the basic idea of an omega for the crash recovery model? The idea is that we always elect a process that has failed and recovered the lowest number of times, and among these we will take the one with the max rank. And we have to have an implementation that guarantees this. So how to do this? So each process counts the number of times it has crashed, and using heartbeats, a process, when recovered, always distribute this epoch, the number of times it has crashed, periodically to all other processes. And we elect a leader with the lowest pair epoch and rank. So if we have two processes with the same epoch number, we select the one with the max rank. So the implementation looks like this. It's similar to Diamond P and omega for the crash stop. It's just, as I said, we piggyback the epoch number with heartbeats. So each process will store the epoch number in its persistent store, and upon recovery it will load the epoch number and increment it and then send it in the heartbeats. And that concludes omega for the crash recovery model.